Hello, this is Dr. Christy Lukes, and we're going to be starting to look at error analysis. In this particular video, we're going to be looking at measurement error specifically. Now, you've covered a lot of this, probably for years you feel like you've known this. Now, the first thing we want to talk about is the difference between accuracy and precision. So accuracy is the extent to which your measurement is close to the true value. And if you don't know what the true value is, this actually may be really difficult to determine. Precision is how exactly you can measure whatever it is, okay? So precision, if I say it's 3 p.m. or is it 3:02 and 45 seconds, okay? But being more precise doesn't mean you're necessarily more accurate. Okay, that precision may be phony, let's just say. Okay, but accuracy and precision, I think, are terms that usually at this stage most students are fairly comfortable with. Now we have two other ways of talking about things that we want to do, and this is about uncertainty. So we have two different types of uncertainty. One is the random error or statistical uncertainty, and then there's systematic error or systematic uncertainty. Okay, the statistical uncertainty is really the key issue that we try to, get better equipment to do this better. Okay, but every time you measure something, it's just a little bit different. Okay. And so we can do things like take a standard deviation of all of our data, and that gives us an estimate of how precise the data was. Now, if we want to turn that into error, we can approximate that using standard deviation divided by the square root of the sample size. Okay, and then that gets us an error estimate. But this is based on the randomness of measuring the same thing multiple times. Systematic uncertainty, really we try to avoid this in the lab, but basically it's anything that wasn't statistical or random error. Okay. Generally, these are things that are due to something like, I don't know, the other day I walked past a lab, not in our department, but I saw a student that was holding a measurement device up and looking at it, trying to figure out what the volume was. He was holding it above his eye level, and he was holding it. So who knows how, angled it was or whatever. Okay. That's going to contribute to systematic error. All right. So we want to try and minimize that by remembering to zero our readings, from a meter, learning how the equipment works properly, putting a graduated cylinder on a level, steady surface, and then getting down at eye level to read from it. Bothering to include barometric air pressure when we're doing our pressure. Do we just say it's 14.7 psi all the time? Okay, and then there's those gross errors, which are kind of called stupid errors. Okay. Now, these, hopefully, we will minimize those in our procedures or processes, okay? But we will never be able to get rid of the random errors. Those are always going to be there. So the experimental procedure is one place where we can look to see if there's a way to minimize this. So how a gauge is read, determining the endpoint of a process. Oh, some people really struggle with those titrations, right? Recognizing whether it's the endpoint or not. Calculational propagation. So I have this quantity I measured and this quantity I measured, and now I'm going to do math with those two. What is the error in that answer? Okay. So we're really looking more on just those single variables today in this lesson. So those procedural errors, Generally accepted is that you can read 1/5 of the smallest graduation if you really, really look at it. So you're reading a burette, and it's a nice tiny little diameter there, and it's in 0.1 milliliter increments. And if you really get down at eye level and you've got everything set up right, you can probably read it to the nearest 0.02 milliliters. Okay? And so therefore your measurement that you take is going to have those two decimal places, plus or minus 0.02 milliliters. Okay? A digital meter, probably you should assume that it's the smallest increment reported. Okay? So if the thermocouple readout says 0.1 degrees C, then 75.2 plus or minus 0.1 degrees C would be the correct way to read that. Pressure gauges are a little bit trickier. Generally, they are considered to have 1% of their full scale as their error. Okay, so a 0 to 100 psi gauge would have 1 psi error. Okay, we're going to have a readout from a low pressure gauge. I don't remember if it's like a 2 or a 5 psi gauge, say 5, then 1% of 5 is 0.05 is the most you can read. Now notice that these measurements are all based on that it's there and it's held steady long enough that you can really study and make sure you're reading it precisely. Okay? We're going to be doing a lot of readings on things that are happening fast. And in those cases, it's going to increase our error. This is the precision that we can get from our device, but that doesn't mean that that's the precision you get from the experimental reading of that device. Okay, so if you have a pressure gauge on something and you have it fluctuating back and forth between 2.1 and 2.3, okay, well, then, okay, you're going to maybe report 2.2 plus or minus that 0.1. All right, don't worry if the gauge said that you could have read it to 0.05. That's if it was holding steady. Okay, so these are going to be the minimum errors, but not necessarily what you want to report. You're going to need to use judgment for things that are in motion and have noise. So various things that we were going to measure. Let's just look at this one, assuming that we had a micrometer. Okay, so I can take multiple measures of this little device and crank it down. And I measured the length of something 3 times. I got 12.279, 11.781, 11.685. Okay, now when I read this, it's to 0.001 millimeters. Okay. That's the least error I have, all right? Now, if I do the average calculation on this, I get 11.915, right? Just add up the 3 values and divide by the number 3, and I get 11.915. The standard deviation for this, I'm going to subtract the mean value from each of those, square them, and then divide by n-1, square root of that. Fortunately, Excel does those calculations for me, so I don't. Anyway, 0.319. And the error, I'm going to take that standard deviation and divide by the square root of 3, and so 0.184. So, and yeah, 4 or 5, I don't know, one of the two is a typo. So I could report this as 11.915 plus or minus 0.185, but that's crazy because my error, everything after that first digit on my error is garbage. That's hidden within the error. So what I'm going to do is I'm going to round this to 0.2 and make sure that the value at the front, if I'm only going to 0.2, I only get to the tenths place in the first number. So I would report this as 11.9 plus or minus 0.2 millimeters. All right. Now again, the device read to 0.001. That was not my error. Now, another interesting thing that has come up in the past is someone measured something 3 times. They got exactly the same value all 3 times, and so they said that their error was 0. No. It's the smaller, or it's the larger of either the precision of the device, in this case 0.001 millimeters, or this error that we calculated based on standard deviations. Okay, so the larger of those two is the error. It will not be 0. So one last thing is that sometimes we are going to have to use reasonable estimates for the error. Okay, so maybe you are taking readings at a time specified by your lab partner. So in one of the experiments that we have done in the past, we were running water through a pump and catching that water, and then at a certain time you would shift to a new cup, okay, and your partner tells you to shift. And then the teams were saying that, oh, well, my error that, we recorded this, and so therefore I know exactly what the time was when we made that shift. Okay. How about that time while you were in transition? Probably the error is a little larger than most people were estimating. I was getting some bizarre things like 0.001 seconds. Your reaction time is not 0.001 seconds. Okay? 0.2 is probably a little bit more reasonable. Okay? When you're doing these wild guess errors, try to figure out ways to minimize them. Video recording of your experiment is one way to do that. Okay? But don't underreport your error. Okay? That just causes all sorts of misunderstandings later in your analysis. So this concludes our discussion of measurement error. We're going to look at propagation of error in our next lesson. Thank you.